I guess I need to figure out a way to come back. Let me try this. No. No. Oh, made it. Just in time to cover hyperbolic functions, but of course, first let's get rid of the ukulele. Easy enough. Hyperbolic functions are perhaps the first topic that maybe you haven't encountered yet, and this is great because you're going to learn even more than from the other topics. It's really interesting to think, as we'll see, that even though hyperbolic functions are just defined in terms of exponentials, they actually share a lot of the properties of trigonometric functions. First of all, let's write them down, and let's not call them names yet. Just before we define the hyperbolic cosine and hyperbolic sine, let's look at the basics. What if you're like completely bored and you start playing with exponential functions? Now, the simplest exponential function that you could write would be e to the power of x, right? What if you just add another exponential, but you add e to the power of minus x, which is probably the closest, simplest exponential that you can write. You just flip in the sign. And for some reason, let's say you want to kind of get an average between both, and you divide by 2. It turns out that this that we just wrote is the definition of the hyperbolic cosine. We write it as cos h of x, and it is defined in this way in terms of exponentials: e to the power of x plus e to the power of minus x divided by 2. Now let's say that you play around with another combination of e to the power of x and e to the power of minus x, which is, instead of using plus, we use minus. Let's say we do that and write e to the power of x minus e to the power of minus x. And again, we're sort of taking the average between both components, but in this case we're subtracting. Not really an average, but go along with it. Turns out that this is the definition of what we call the hyperbolic sine. This is written as sine h as the hyperbolic sine. This is cos h, or hyperbolic cosine. The history behind this is not so important, but in case you are curious, it turns out that these terms started coming up in a lot of solutions for differential equations hundreds of years ago. Actually, so common that people started studying them on their own, and this is how people realized that these functions actually share a lot of properties with trigonometric functions. And this is a very nice reason for why we call this cos h and this sine h, or hyperbolic cosines and sines. And it turns out that just like for trigonometric functions, there is also a fundamental identity linking cos h square and sine h square. For trigonometric functions, we know that if you take the square of cos x plus the square of sine x, you get 1. This is for trig. For hyperbolic functions, there's a very similar relation, and this is the first word of caution. Relations are very similar, but sometimes they come with a difference in the sign. In this case, for hyperbolic functions, the identity is cos h squared minus sine h squared is equal to 1. These are for hypers, just to make it sound cool. The great thing about hyperbolic functions is because they are given in terms of exponentials, and exponentials are very easy to manipulate and differentiate, then you can already learn a lot about these functions, even if you've never encountered them before. For example, it is relatively trivial, and I'll leave this up to you. You can also check the lecture notes with an example of how you would prove this. It's all about just subbing in with a definition and showing that once you do that, you end up with an identity, something like 1 equals 1, which would show that this is correct. If you start out with a plus, you will end up with something that does not satisfy the equals 1. In a similar way that we can define an hyperbolic cosine and hyperbolic sine, we can also define the hyperbolic tangent, the hyperbolic secant, or the hyperbolic cosecant, which have definitions that are essentially the same as for trigonometric functions. But let's have a look at them. In a very similar way that you would write that the tangent of x is equal to sine x over cos x, then the hyperbolic tangent, which we write tan h, is also given by the equivalent functions sine hx over cos hx. The same thing will be valid for the hyperbolic cosecant and the hyperbolic secant, which with a little bit of physics 101 magic I'm making appear here. And you can also see them in the lecture notes. Because of this, and just like you can see here, as all of these functions are defined in terms of exponentials, you can always manipulate them. And actually, provided that you know these definitions, you can always make up all the others, essentially almost from first principles. You don't really need to memorize what the hyperbolic tangent or the hyperbolic secant or cosecant are in terms of exponentials. What I would really recommend for you to do is to remember the definition of hyperbolic cosine, that's with a plus, and the hyperbolic sine minus, and just think the obvious simplest exponentials are the one with an x, and then after that the one with minus x, and you can always derive all others. The other really great news is that these functions are incredibly simple to differentiate because it's all about differentiating exponential functions.